According to the National Electrical Code, specifically Section 250.50, grounding to rebar in concrete slabs is sometimes required in single-family dwellings. Let's examine two scenarios. Firstly, when the service enters the garage first, and secondly, when the service enters the house first. If the service enters the garage first, you must ground the service to the rebar in the garage slab. However, it is not required to ground to the rebar in the house slab. Conversely, if the service enters the house first, you must ground the service to the rebar in the house slab. It is not required to ground to the rebar in the garage slab in this case. The purpose of grounding to the rebar in the concrete slab is to provide a low impedance path for fault currents to dissipate safely into the earth. The rebar in each slab is connected to the grounding system. Therefore, it is not necessary to ground to both slabs. When the service enters the garage first, grounding to the garage rebar provides a sufficient path for fault currents. Grounding to the house rebar becomes unnecessary. Conversely, when the service enters the house first, grounding to the house rebar provides a sufficient path, making it unnecessary to ground to the garage rebar. There is, however, a note to consider. If the slabs are poured at different times or by different contractors, it is recommended to add a bonding jumper between the rebar and the two slabs. This ensures a continuous grounding path. The rebar used for grounding must be at least 1/2 inch in diameter. It must be bent or welded into a U for ground. The U for ground, also known as a concrete encased electrode, is a grounding electrode created by encasing a length of steel rebar or a bare copper conductor within concrete. It's a very effective method for providing a low impedance ground connection. The National Electrical Code, or NEC, outlines the requirements for U for grounds in Section 250.52 A3. This section specifies the requirements for concrete encased electrodes. The electrode must consist of at least 20 feet of 1/2 inch diameter or larger steel reinforcing bar or 4 AWG or larger bare copper conductor encased by at least 2 inches of concrete. The concrete must be in direct contact with the earth. This is typically achieved by placing the rebar or conductor within the footing or foundation of a building. The purpose of a U for ground is to provide a reliable and low resistance connection to the earth. This helps to dissipate fault currents and minimize the risk of electrical shock. The large surface area of the concrete encased electrode provides a greater contact area with the earth. This results in a lower impedance ground path compared to other grounding methods, such as ground rods. Installing a U for ground typically involves placing the required length of rebar or copper conductor within the concrete forms before the concrete is poured. The rebar or conductor should be securely fastened to the forms to ensure that it remains in the correct position during the pour. Once the concrete has cured, the U for ground is connected to the building's grounding system using a grounding electrode conductor. The grounding electrode conductor must be sized according to the requirements of the NEC, based on the size of the service entrance conductors. Regular inspection and testing of the U for ground is important to ensure that it remains effective. Over time, the concrete can crack or deteriorate, which can compromise the integrity of the ground connection. Periodic testing using a ground resistance meter can help to identify any potential problems. If the ground resistance is found to be too high, repairs or replacements may be necessary to maintain a safe and effective grounding system. In summary, a U for ground is a highly effective method for providing a low impedance ground connection. It involves encasing a length of steel rebar or bare copper conductor within concrete that is in direct contact with the earth. The NEC provides specific requirements for the construction and installation of U for grounds to ensure their effectiveness and safety. Proper installation, inspection, and maintenance are essential for ensuring that the U for ground continues to provide a reliable path for fault currents to dissipate safely into the earth. Grounding electrode conductors connect the grounding electrode to the electrical system's grounded conductor or equipment grounding bus. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors. Bonding jumpers are used to connect different metallic parts of the electrical system together to ensure that they are all at the same electrical potential. This helps to minimize the risk of electrical shock. Bonding jumpers are sized according to NEC Table 250.102. D1. Equipment grounding conductors provide a path for fault current to flow back to the source in the event of a ground fault. This allows the overcurrent protection device to trip and de-energize the circuit. Equipment grounding conductors are sized according to NEC Table 250.122, based on the rating of the overcurrent protection device. When installing grounding and bonding systems, it is important to follow all applicable requirements of the NEC. This will help to ensure a safe and effective electrical system. Here are some additional considerations for grounding and bonding. Firstly, use corrosion-resistant materials. Grounding and bonding conductors and hardware should be made of corrosion-resistant materials to ensure long-term reliability. Secondly, protect grounding conductors from damage. Grounding conductors should be protected from physical damage by routing them in conduit or other protective raceways. Thirdly, maintain continuity of grounding paths. Ensure that all grounding connections are tight and secure to maintain a low impedance grounding path. Fourthly, inspect grounding systems regularly. Regularly inspect grounding systems for signs of corrosion or damage and make repairs as needed. Fifthly, document grounding systems. Keep accurate records of grounding system installations and modifications. Understanding grounding and bonding requirements is essential for ensuring electrical safety. By following the requirements of the NEC and paying attention to detail during installation and maintenance, you can help to protect people and property from electrical hazards. When dealing with electrical systems, always prioritize safety and consult with a qualified electrician if you have any questions or concerns. Grounding and bonding are critical components of a safe electrical system, and proper installation and maintenance are essential for protecting against electrical shock and fire hazards. Always refer to the latest edition of the National Electrical Code and local electrical codes for specific requirements and guidance. These codes are regularly updated to reflect the latest safety standards and best practices. In addition to the NEC, other standards and guidelines may apply depending on the specific application and location. For example, IEE standards may provide additional guidance on grounding and bonding in industrial facilities. It's also important to be aware of any local electrical codes or regulations that may be in effect. These codes may impose additional requirements or restrictions beyond those specified in the NEC. Understanding the applicable codes and standards is essential for ensuring that electrical systems are designed, installed, and maintained in a safe and compliant manner. Proper grounding and bonding are fundamental to electrical safety, and adherence to relevant codes and standards is crucial for protecting people and property from electrical hazards. Furthermore, remember to use appropriately rated tools and equipment when working on electrical systems. Insulated tools, safety glasses, and other personal protective equipment should be used to minimize the risk of electrical shock or injury. Always de-energize circuits before working on them, and use a voltage tester to verify that the circuit is de-energized. If you are not qualified to work on electrical systems, consult with a licensed electrician or other qualified professional. Electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others. Safe work practices, combined with a thorough understanding of grounding and bonding principles, are essential for ensuring electrical safety. In summary, grounding and bonding are critical aspects of electrical safety. Understanding the principles of grounding and bonding, adhering to the requirements of the National Electrical Code and other applicable standards, and using safe work practices are all essential for protecting against electrical hazards. Always prioritize safety when working on electrical systems, and consult with a qualified professional if you have any questions or concerns. Proper grounding and bonding are fundamental to electrical safety, and their importance cannot be overstated. By following the guidelines outlined above, you can help to ensure that electrical systems are designed, installed, and maintained in a safe and reliable manner.